Okay, welcome to a refresher session for the UNR Math Center. My name is Cameron, and this refresher session will cover sets and specifically sort of the fundamentals of set theory. So this could be useful for classes such as Math 295, Math 302, as well as Stat 152, Stat 52, and maybe even Math 120 and some of those courses where you start learning about using sets. So I guess we'll begin by, so the first thing I want to talk about is what is a set. And so a set is defined to be so I'll say a set is a collection of unique, unordered items listed between braces. And so let's kind of unpack what I'm saying here. So for example, the set that we call A, denoted as the following, 1, 2, 3, 4, is an example of a set. And let me fix this brace here a little bit. That doesn't look too good. Okay. So what I mean by collection of items, these items happen to be numbers. So we have 1, 2, 3, 4. However, sets can also contain letters, symbols, even other sets. So one example that I have here is containing numbers, and unique meaning that no item is repeated, and unordered meaning that this is the same as the set 4, 2, 1, 3, right? These are the same because they contain the same elements. Their order in which they're listed does not matter. So if I call, I guess I should say A, B, and A and B are the same set. We'll say because they have the same set of elements, their order does not matter. Another thing we'll say is that an element, we'll say, sort of the definition of this, an item contained within a set is called an element of that set. And we use the notation 1 is an element of A with the symbol, the sort of pitchfork symbol, meaning is an element of. I shouldn't have, let's not put parentheses around, I'm sorry, quotation marks around the symbol. This pitchfork symbol means is an element of, and so we would use the notation 1 is an element of A if we were talking about for the given set above, right? So any value sort of separated by a comma here is an element of the given set. You could also say 1 is an element of, and actually write the whole set between braces as well. That also works. But when you have a named set, oftentimes we will just sort of use that. Oh, what's going on here? Let's fix this. So you could say, or 1 is an element of 1, 2, 3, 4. Right, these both make sense here. You could say 1 is an element of A or 1 is an element of the set. They both mean the same thing. And then like I sort of iterated earlier on, we'll say note sets can contain more than just numbers. They can contain symbols, such as mathematical symbols, for example, letters, and even other sets. among other things. These are just some of the most common things you might include into a set. So for example, you could have a set containing another set. You could have it contain something that's called the empty set, which we'll touch on later. So for example, this would be a set containing the set 1, 2 as one of its elements, 3 as its other element, a letter E, and the empty set as another one of its elements. And so I guess notation, I'll note, oops, is called the empty set. So it's just a 0 with the line through it, which is denoted the empty set. Also written sometimes just a set of braces when deleting them. Okay, so the idea here is sets a unique collection of unordered items listed between the set of braces. An item with a contained within the set is called as an element of that set. And you use the pitchfork sort of symbol to denote that something is an element of a given set. If it's not, then you could also do, so 5 is not an element of A. So putting a line through it means not. So we're sort of saying not an element if we just put a line through the element symbol or the pitchfork symbol. Denotes five is not an element of A, right? The set A. So that's something else I should have as a little bit of an example. Okay, so using this, I think we can go on to some more common thing, some more complex things. So we're going to talk about set builder notation next. Okay, so set builder notation is often used for sets containing an infinite for sets containing an infinite number of elements. And so what I mean by set builder notation, let's just sort of use an example. The set of all integers which are even, or yes, so the set of all even integers, I'll just write this, is denoted as, so we'll say the set of all, I'll say x in, so we're using that element symbol, z, where z here is the set of integers, and I'll write out what that is in a second, but we commonly refer to this as sort of z. So all x and z such that, that's what this colon reads. So whenever you see a colon in set builder notation, it's sort of this condition that the left property or the value to the left of it has to satisfy. So x and z has to satisfy that x is equal to 2 times n, where n is also some other integer. Right? That's sort of one way of denoting an even number. If it was odd, we would sort of do 2n plus 1 is how we denote an odd number. So this is the set of even integers. And z here is denoted as sort of the set. Another way we often write sets is we'll do, if they're infinite, but they follow a pattern, you could sort of do a dot, dot, dot. And then I'll say -2, -1, 0, 1, 2, dot, dot, dot. So we see this pattern is just every possible integer, 0, 1, 2, 3, 4, up to infinity, and then -1, -2, -3, down to negative infinity in the opposite direction. Another common set we work with is, that you'll see, is the set of natural numbers. And that's sort of the set 1, 2, 3, dot, 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 on to infinity, right? These are sort of all positive integers. This is all positive negative integers and 0. or what these two sets sort of represent. So this is a set of what's called natural numbers, and this is the set of integers, which we often use in set type questions a lot. Another type of way that you could use set builder notation is an interval, for example, from -2 to 2 can be written as follows. So you could describe this as the set of all x in R, where R is just the set of real numbers. You might have seen this in Math 120 or Math 126, somewhere around there, when you're sort of writing your intervals of values in set builder notation, and you would do something like this, right? So it's a set of all real numbers where it's between -2 and 2. These two things mean the same thing. So you can always write intervals as sets, and that's one common way you might see them. So that's just like another example of set builder notation and where that would come into play. So the idea with set builder notation is you have some value on some condition on the left, so it's all x and z or all x and r in this case. Colon reads such that, and then the right is sort of the condition that that left value has to satisfy in order to be in the set. Namely, in the first case, it's that it's equal to 2 times n for some other integer. In this case, it's that x is between -2 and 2, right? And the reason you would use set builder notation here is because remember, when real numbers, there are like infinitely many real numbers between -2 and 2, right? Because we have a lot of irrational numbers between those, as well as almost an infinite, I believe an infinite number of rational numbers as well between any two integers. So it's always important that we use set builder notation in these cases because it would be hard to write out every single element in that set. In fact, it would be impossible because there are infinite number. So set builder notation is one way in which we do that. Okay, the next topic that we'll glance over now, so that was just the one way that sets are often used. We're going to talk about the cardinality of a set. And so I guess I don't need to capitalize this. So the cardinality of a set is the number of elements in that set. So this is most commonly used when you're talking about sets of finite length, although technically you can have a set of infinite length. Its cardinality is infinity, but we sort of have an interesting property that you'll get learned in Math 295 if you take that, or Math 302, that there are sort of different types of infinities when talking about cardinalities. So for this sake, we're just going to focus on sort of finite sets. So for example, I'll just use, if A is equal to the set 1, 2, 3, 4, 5, 6, right? The cardinality denoted, we just put sort of absolute value bars around the set to denote its cardinality. This cardinality would be equal to 6, okay? So the number of elements in that set. Another example, if we had, let's say, a set, I guess I'll use something other than A here. I'll use B in this case. 1, 2, the set containing 3, 4, 5. So remember, the set here is an element of that set. E, F, G, something like this, where I have sort of this mixed set with letters and numbers. And so the number of elements, if you have sort of these nested sets, the way I look at this is I'm going to count the number of commas. Like we're looking inside of one set of braces, right? So we have each comma separating a value inside one set of braces. So we have 1, 2, this is 1, 2, this whole set here is one element, E, F, and G. So we have 1, 2, 3, 4, 5, 6. So the cardinality B here is also equal to 6 because we count this entire set containing 3, 4, 5 as one element within the set B, right? So this is an example of a set being an element of another set. So whenever you're finding the cardinality of a given set, you just look one set in, sort of, or one set of braces within. Okay, and let's just do another example just to make that even more clear. If we had C as the set containing 1, 2, 3, 4, 5, 6, and then we'll say the empty set is an element of this as well. number of the cardinality of C, so the number of elements, sorry, in our set C is equal to, well, we have 1, 2, this whole set is another element, 3, 4. Okay, so this set would contain 4 elements. And so remember the cardinality, we just use a sort of absolute value bars or straight line bars around the set to denote its cardinality, and it's always going to be some numerical value for finite sets. Okay, when I say finite, I just mean there is a fixed number of elements, right? Not an infinite number of elements. That's the difference between infinite and finite. Okay. So this is, I guess, gives us so a little introduction to cardinality. And where this is really useful is when talking about subsets of a given set, and also, I guess, the power set of a given set. And I'll sort of talk about what those are. Okay, so subsets of a set. So a subset of a given set, we'll say A, is a set which contains or I guess I should rephrase this, is a set whose elements are elements of A. So a subset of a given set is a set where all of the elements of that subset are also elements of the set of A. So an example of that would be if A is equal to the set 1, 2, 3, 4, and B is equal to the set 1, 2, 3, we'd say that B is a subset of A, and we use this symbol here. So we use symbol or, so it's sort of like a C or like sideways U, basically. So almost like a less than sign, but sort of a U instead of a point at the end. So you can use one of two symbols. You could use, technically we could use the symbol with this U and a line under it, but a stronger argument would be, so we say that B is a subset of A, and if B is a proper subset of A, we say B is a subset of A. So we don't put the line underneath it. It's kind of like less than or equal to, right? You could always use less than or equal to if something is less than another value, but it's a stronger condition to just say that it's less than that value. And we sort of would do that with our set here. So for example, B is a subset of A, but it's also a proper subset of A because it's not equal to the set itself. I guess note the set A is always a subset of itself, but not a proper subset. Give me 1 second here. Yeah, okay, I'm just spelling this wrong. Sorry, I'm a math major, not a English major. There's one P. There's not two sets of P's next to each other in proper. Okay, so set is always a subset of itself, but never a proper subset of itself. Okay. So you use sort of the subset with the line under it if it's just a general subset. And if you know it's a proper subset, then you could use this other symbol. They both work. I often just use the sort of subset with the line underneath it symbol, but you could use either if it is a proper subset. Okay. Um, okay. I guess the last thing to talk about is another note. And this is a super useful note. So a given set A, or I'll say B in this case, because I have A written there, has exactly 2 to the power of m subsets if m is equal to the cardinality of that set. So any set has 2 to the m subsets where m is the number of elements in your set. This is a super useful property. So we could say, example, the set, say S equal to ABC has 2 to the, well, the cardinality of S is 3 because it has 3 elements. 2 to the 3 equal to 8 subsets. And we could actually list these. So these include, it shouldn't be too hard since this has 3 elements. So the first and foremost, the set containing A, B, and C. So the set itself is a subset of itself, as we stated in this note. Then we have, I guess, the collection of sets that contain only 2 of the elements. So we have the set containing A and B. Oops, what happened there? The set containing B and C. We have the set containing A and C. A and B, B and C, A and C. We have the singleton set. So we have the set just containing A, the set just containing B, the set just containing C. And then lastly, the other value that's always a subset of a given set is what's called the empty set. Right? So you can have the set containing no elements is trivially a subset of any given set. And so that's why that symbol I used earlier was super useful. Because when we're talking about subsets, the empty set is always a subset of a set. Sometimes it can be hard to sort of write out all these possible subsets, especially when the number of elements in your set gets larger and larger. But there is this theorem and the super useful note here that for a given set, its number of subsets is equal to 2 to the m if m is the cardinality of that set. Okay, so here is an example of that. Another super useful thing here is what we could talk about is power sets. So the power set of a given set S is the set containing all subsets of X. Right, so like in the last example, right, we found all the subsets of a given set. Also, I said we denote this as, they sort of use this script P, power set of S equals, or I'll just say power set. So that's what we denote, or the notation we use when talking about the power set. So if S is equal to the set, I'll use in the last example A, B, C, the power set of S is equal to the set containing each element is a subset of this set. So the set itself is one subset. The set containing each combination of 2 elements is a possible subset, right? A and B, B and C, and then A and C. Oops. Okay. Next, we have the singleton set. So the set just containing A, the set just containing B, and the set just containing C. And then lastly, the empty set. Right, that's what this is. And if we count this up, this should equal 8. Remember, because the cardinality of S is equal to 3. So 1, 2, 3, 4, 5, 6, 7. I have 8 elements. So we could say that the cardinality of the power set of S is equal to 8, which was 2 to the 3, right? So the cardinality of the power set is just equal to the number of possible subsets of a given set, because the power set is the set of all possible subsets. So that's another thing that we sort of might construct. The last little bit that I'm going to talk about now, so that was a lot of sort of notation that we use when talking about sets, is we're going to talk about these ideas of union and intersection of two sets, difference of a set, what set difference means, and then also the complement of a set when we're talking about relative to a universal set. Okay, so I'll do union, intersection, difference, and complement. So let's say we're given two sets. So I'll do a set A, B, C, D is one set, and we'll call B another set, A, B, E, F. So the union is the set containing all elements found in A, B, or both A and B. Right, so the union of two sets is the set. Remember, a set is a collection of unique items, so we don't double count anything, but it's any value that's in A, B, or both. For example, A and B are in both A and B, so they will be, by definition, in the union. So we denote this A union with B, so it looks like a, sometimes this is called cup. A union B, like so. It's like a U, but there's no sort of line at the back, like when we draw a U often. So A union B is a set, and it contains A, B, C, because C is an A, D, because D is an A, and then E and F. Right? All values that are found in A, B, or both. So A and B are in both, so we'll include them. C and D are in A, so they'll be included, and E and F are in B, so they'll be included. We don't include anything else, right? If anything is, like, for example, G is another set, so it will not be in there either. Okay? The intersection is the set containing all elements found in A and B. So the intersection, we'll denote this with a cap, so it's like an upside down U, kind of. It's the upside down version of the symbol we use in union. A intersect B is equal to, again, it's a set. It's only the values that are found in both sets. So in this case, A and B are both in set A and set B, and I know that's kind of confusing based on how I noted this, so I apologize for that. So maybe I'll call this I should call these sets something else. Let's call these V and T. Why not? So for sake of simplicity, we'll do V union with T and V intersected with T. And just so I don't confuse you with the A and B's that I was writing there. Note, it's important that the intersection can be empty. For example, if these sets shared no elements, so example, A equal to the set 1, 2, 3, that's a set. B equal to the set 4, 5, 6, right? A intersect B is equal to the empty set, or if you want to use just the braces with nothing between them, those both work because they share no elements, right? Their union would be 1, 2, 3, 4, 5, 6, but their intersection in this case is empty because they share no elements. So that is also a possibility. Keep that in mind. The complement, so Actually, let's do difference first, because this one could be a little tricky. So the difference is the so I guess so you could denote the difference v minus t, or sometimes use a backslash to denote set subtraction. And the reason I'm using this notation here is because it's sort of important which set we're talking about. So, and we're talking about with regards to these two sets, v and t. The difference, v minus t, is the set of all elements in V that are not in the set T. So V minus T would be the set C, D, right? So it's important to note that your elements in a set V minus T are only going to be elements that are in V to begin with. So if you see anything that's in V minus T you're writing down that's not in V to begin with, then you probably did something wrong, or you did do something wrong, I should say. So it's an element that's in V, and you basically look at the set V, we have A, B, C, D, and we subtract off the elements that are also found in T. So since A and B are both in T, we remove them from V to get V minus T, or the difference of V and the set V minus T, okay? Even though E and F do not occur in V, it doesn't really matter because we're just subtracting off from V the elements that are also in another set. So we kind of don't care about the other elements in T that are not in V when we do this. If we want to find T minus V, it's the same sort of idea, but now our set we're looking at is T, so it's going to contain only elements that are in T to begin with that are not in V. So the only elements in T that are not in V are E and F, so this is what this set would be denoted as, right? Because again, we only remove A and B, because A and B are the only elements that are in T that are also in V. So even though C and D are not in T, we don't put them in the set, because this set is only the elements that are in our original set that are not in the other set. Okay, so that's what it means for set when we're working with set difference. Okay, so there's an important distinction there. And then I guess the last thing we'll talk about, I guess I'll do that on the next page since we ran out of space, is complements. And so given a universal set, so we need to work with a universal set in order for complement to make sense. I'll say U equal to, and we'll just do 1, 2, 3, 4, 5, 6, 7, 8, 9. We'll just do 1 through 9 as our universal set. And a set, I'll say A equal to 1, 3, 5, 7, 9. So this is sort of all those odd digits. The complement of the set A relative to the set U is the set of all values in U which are not in A. So if we want to find a complement, so we'll denote it as, or sometimes it's denoted with a line over the top. I also see sometimes it's denoted with a prime symbol. You can a lot of things, different things are used, but it could be any of these notations. This is the set. Basically, it's everything in U that's not an A. So that would be 2, 4, 6, and 8, right? Just the even sort of digits I have here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Remove the values in A. That's the complement. So the complement is always relative to some larger set. Otherwise, if we don't know what that is, it's sort of ambiguous as to what this complement would be if we don't know what our universal set we're working with is. Um, and so, right, another example is if you're working with intervals, so the complement to, I guess, a closed interval, we'll say -3 to 3, right? Remember, well, before we write that, remember this is equal to the set of all x in the real numbers, such that -3 is less than or equal to x is less than or equal to 3. So if we want to find the complement, it's basically everything outside that. So if we think about on a number line, right, between -3 and 3, our set we're dealing with is all values in here, right? So a complement of that is just relative to the real numbers is just everything that's larger than 3 or less than 3. So sometimes we still can, right? In this case, it's implied that our set we're working with is the real numbers. So the complement of the interval -3 to 3 is, and we're going to use set notation here, the set of all x in R such that we sort of have, whoops, don't know what happened there. We have sort of two things, right? Either x can be less than -3 or x can be greater than 3, right? These are strictly greater than because 3 and -3 are included in our other set, so they cannot be in the complement. So it's the set of all x that is less than 3 or greater than 3, right? Another way you might note that is, as you may have seen in 126 or something, when working with intervals, you might also denote that as a set from -infinity to -3, unioned with the set from 3 to infinity. This is another way of writing the same sort of thing, right? Where we're using that union idea here between two different sets that are actually intervals in this case, right? -infinity, -3 is a open interval, union with another open interval. And because these intervals are actually sets, this idea here should make sense, right? We're taking the union of two sets, really. Okay. So that's another idea there. And I think, so we covered this. I think we covered sort of the basic idea or overview of all these ideas. Hopefully that gave you some refresher from when you may have learned this in Math 126, 127, and give you some insight into maybe some Math 295, 302 sort of concepts. So we'll maybe continue this in a more advanced set theory refresher session later, but hopefully that gave you some hope, and have a good one.